Assalamualaikum and a very good day to my supervisor, Dr. Muhammad Izami, to my internal and external examiner, Dr. Nawahyu, and also to Mr. Muhammad Farmizam. So my name is Zarfan bin Hisham, and I would like to present my final year project titled Esterification of acetic acid to methyl acetate using zirconia supported on SBA15 catalyst. So the project consists of 5 chapters. So the first chapter would be the introduction of the study and also the objectives for the project, and also followed by the literature review. And then for chapter 3 is the methodology on ways to conduct the study, followed by results and discussion, and then finish with conclusion and some recommendations. So the basic would be the esterification process. So basically, esterification process is a reaction between carboxylic acid and also an alcohol in order to produce ester and water as byproduct. So the study uses acetic acid react with methanol in order to produce methyl acetate. So basically, there are 2 types of catalysts widely used as according to the study conducted. So the first one will be the homogeneous catalyst, and also the second one would be heterogeneous catalyst. So few examples of homogeneous include sulfuric acid and also hydrochloric acid, while heterogeneous include Amberlist type of catalyst and also indium type of catalyst. So few application of methyl acetate include in the paint industry, where it is used in the manufacturing of lacquers. Second would be the epoxy resin coatings. The third one would be in the cosmetics industries for the production of nail polish remover, and last but not least in the textiles industries for the manufacturing of dye. So the problem statement of the project is the limitations of catalysts from previous study. For homogeneous catalysts, it tends to corrode the environment and also to corrode the reactors. And then it is also difficult to separate the catalyst for reuse purposes, and also it tends to produce side reactions. Like an example, when hydrogen iodide is being used as catalyst, it tends to produce methyl iodide when react with methanol. And then methyl iodide is the byproduct which is not favored. And then for the heterogeneous catalyst is the pore distribution, where some of the catalysts are quite small in terms of its pore distribution. So that brings me to the catalyst used in the project, which is zirconia plus SBA15 as catalyst. So it is basically a well-ordered network, possesses strong acid sites, and also it can be reused, and last but not least, it can be used also in low catalyst loading. So that brings me to my objectives of the final year project, which is to implement mesoporous silica based catalyst SBA15 as a support to solid acid catalyst zirconia on the esterification process. So the scope would be to synthesize the catalyst itself and also conduct the characterization process, and then it is followed by the study of esterification response and optimization of the reaction parameters using response surface methodology method in design expert software. So moving on to the details of scope of study. In order to prepare the catalyst, it uses urea hydrolysis method. And then for the characterization process, the method used are nitrogen desorption analysis. The second one would be transmission electron microscopy in order to form an image of the catalyst. And then the third one would be scanning electron microscopy in order to scan the surface catalyst. And then last but not least is the titration method for the determination of catalyst acidity. For the catalyst prediction and optimization, the identified important parameters include molar ratio of acetic acid to methanol, the catalyst loading, and also the reaction temperature for the reaction process. Moving on towards the literature review, so the first part of my research would be identifying previous reaction process using zirconia on SBA15 as catalyst. So there are few types of different esterification process. What I can conclude is that the catalyst converts the product at high conversion, but it involves additional acid like sulfuric acid and also silicotungstate acid for a much higher conversion. Second part of my research include to identify esterification of acetic acid to methyl acetate, but using different types of catalysts. So I have ranked the catalyst from low conversion at 56% acetic acid conversion to highest conversion at 69% using Embellis 36. So the findings would be the acidity, moisture content, and pore distribution played a major role for acetic acid conversion. So the main core of my final year project will be the response surface methodology. So it is basically a multivariate technique for analytical optimization. It will require dependent variables like the experimental data, acetic acid conversion, and also independent variables like temperature, catalyst loading, and molar ratio. So it consists of experimental design that from matrix composed by different level combinations of variables. One of the study that uses RSM method is the esterification of acetic acid using Embellis 16. After identifying the level of variables, experimental design been chosen. Then RSM will generate list of factors combinations using low to high value. After experiment have been conducted and conversion identified, it serves as an input to the software for optimization. So the high R squared and adjusted R squared indicate that produce a quadratic model between factors from the software, feed the experimental data, and then conclude that the method used is reliable for discussion process. Moving on to the methodology, to prepare the catalyst is to firstly synthesis the SBA15 catalyst support, and then followed by the incorporation of zirconia into SBA15 using urea hydrolysis method. For the characterization of catalyst, the study requires the usage of few different characterization methods in order to identify the surface characteristics of the catalyst and also to identify the acidity of the catalyst. So the aim for response surface methodology is to predict the experimental conversion from different level of variables combination. So my final year project will be doing optimization step first rather than performing experimental step at the beginning of the project. Since the experimental data conversion would be used from previous study, zirconia SBA15 will be compared with other catalysts to properly predict the catalysis conversion. Then after comparing the acidity and pore distribution with other catalysts, the most close catalytic property will be used as basis for this project conversion. And then the analysis will be carried out using the software for an optimization. So the experimental design will be central composite design, CCD. Then the total number of experiment is 20 runs covering different level of variables, namely center point, factorial point, and also axial point experiment. So proceeding with the methodology, the table on the left side will be the results of pore distribution and acidity of different catalysts from previous study. So in order to identify the right catalyst basis, acidity and pore distribution played a major role for conversion. Thus, Embellis 70 will be taken as first basis due to its closest acidity compared with other catalysts. However, the pore volume of Embellis 70 is very low and could not match the mesoporous SBA15. Thus, reroute of basis towards Embellis 16, although the acidity of Embellis 16 doubles the compared with SBA15 and also zirconia, the large pore distribution of zirconia SBA15 predicted to balance out the acidity, and the choice would be a reliable option compared with Embellis 36. Moving towards Chapter 4, Results and Discussion. So the catalyst characterization data results will be taken from previous student, since the catalysts are readily available in the university. For scanning electron microscopy, Figure 1 shows SEM micrograph of SBA15 at 40 micrometer. So it can be observed that the SBA15 portrays a wheat-like microstructure in overlapping condition at large quantity. For Figure 2, it shows SEM micrographs of zirconia at 40 micrometer. So it can be observed that it portrays the bulkier molecules of the surface in an agglomerated condition compared to SBA15. For transmission electron microscopy, Figure 3 shows TEM image of SBA15, while Figure 4 shows TEM image of zirconia incorporation onto SBA15. Both images are at 100 micrometer scale. So for Figure 3, it can be observed that it consists of hexagonal framework throughout the specimen, and it also shows a mesoporous structure in a uniform manner. While Figure 4, after adding zirconia, the mesoporous structure remains intact. However, there is only a partial dissociation of structure may be seen at small area of catalyst surface. For nitrogen adsorption analysis, which focuses on identifying the surface characteristics of the catalyst, for SBA15 catalyst support, it consists of a very high surface area, pore volume, and pore diameter. And then after adding zirconia onto the SBA15, it can be observed that the surface area decrease. This includes the pore volume. So these results actually supports the previous claim of structure partial dissociation. And then the acidity of zirconia SBA15 is at 2.04 millimole per gram. Moving on to the empirical model, after incorporating conversion results from different factors level, the top part shows final quadratic equation in terms of coded factors, where the letter A represents reaction temperature, B would be the catalyst loading, while C is the molar ratio of acetic acid to methanol. In order to validate the model, ANOVA statistics being used. So from the adjusted R-squared, it shows more than minimum 0.95, indicate the accuracy and reliability of the model itself. So the ANOVA also recognize each factors like the temperature, molar ratio, and catalyst loading to be significant from less than 0.0001 p-value and also a high F value. So for response surface methodology, the factors interaction with each other will be studied in order to ultimately achieve the optimum reaction parameters. So the first interaction would be from low to high catalyst loading and also reaction temperature. So the molar ratio is kept constant at 1 to 3 of acetic acid to methanol. So from the figures observed, the left figure would be the three-dimensional surface contour plot, while the right figure would be the two-dimensional contour plot, where both factors versus the conversion of acetic acid. So it can be observed that there is a wide gap and curvature effect of the surface line at high factors value of this, indicating a high temperature and a high catalyst loading are required for an enhancement of acetic acid conversion. So the second interaction would be the molar ratio versus reaction temperature at a fixed catalyst loading at 0.025 gram per centimeter cube. So as observed from the two-dimensional contour plot, the curvature is not visible as compared with previous interaction. However, there is a presence of wide gap between the contour lines, indicating that high temperature and also high molar ratio would contribute to a much higher conversion of acetic acid. So the third factors interaction would be the molar ratio versus catalyst loading. So the reaction temperature is fixed at 70 degrees Celsius. So as observed from the three-dimensional and two-dimensional contour plot, the curvature dominant at 71% conversion line, while the wide gap observed between contour lines, which basically translate to a high catalyst loading and high molar ratio requirement in order to achieve high conversion of acetic acid. However, at maximum catalyst loading and molar ratio of acetic acid to methanol, the conversion observed to drops down from 77%. This is probably due to more disruption between reacting particles and also the catalyst in order to achieve a successful collision and conversion from a larger area of catalyst loading. So the optimization determination is being carried out by the software. So the solution provided by design expert software for the following variables are as follows, where the temperature is at 75.19 degrees Celsius, catalyst loading is at 0.03 gram per centimeter cube, while the molar ratio is at 1 to 3.8 of acetic acid to methanol, in order to achieve a conversion of methyl acetate at 0.785. So the solution is chosen from a total of 10 solutions. So the chosen optimum is at lowest catalyst loading in order to practically save more costs but obtain the best conversion of methyl acetate. Moving on to the conclusion and recommendation for my final year project. So the conclusion that I have summarized include the catalysts have high pore distribution and sufficient active sites. The response surface methodology quadratic model is reliable with all factors played a crucial role in the conversion. The RSM also able to determine optimum operating parameters and response of the reaction itself. And last but not least, the catalyst loading actually played the greatest role for producing curvature effect and interaction. This is because, as clearly observed in the three-dimensional contour plot, when catalyst loading is being put as the manipulating variable, the curvature effect can be clearly observed. And then to proceed with the future studies for the reaction process for the esterification of acetic acid is to conduct the experimental process according to the list of factors combination from the software at different level in order to validate the optimal operating parameters prediction. And then second one would be to include a second response like yield of methyl acetate. Then the third one would be to add another factors like reaction time in order to study the effect of reaction time and also ultimately to obtain the optimum reaction time for the esterification process. So that will be all from me, and thank you.